Good evening, mathematicians and lay math enthusiasts. My name is Jeff Cook, and this is the fifth video I'm putting together on a direct proof of the Riemann hypothesis. If you've watched the other videos, you will know that in the fourth video, I presented a direct proof of the Riemann hypothesis. The paper is in preprint. It's been there for a few months, kind of out there, letting mathematicians beat it up and look at it, and we're refining it as we go. A couple typos here and there, but nothing major. We do know that today all of the equations are correct. We're letting it go through its process, and we decided that these videos might be a good way to for those reading it to understand where it's coming from. Kind of like me sitting down with you over a cup of tea and discussing the proof. If this is not scripted, so pardon the ums and the coughs or whatever else goes along with that. Perhaps even some outright errors in this conversation. All right, so that's okay because this is unscripted and I want it to be just kind of free flow. And I'm going to present some slides and we're just going to go over them together. All right, a year ago, or about actually, so 2 years ago. Sorry, first mistake right there, and that's okay. All right, about 2 years ago now, almost 2 years, I presented a finding to my friends and colleague Greg Volk and Dennis P. Allen, and which has led to this proof. We got together. Discussed how it might be presented. I asked them if they want to be part of it, and we all agreed, and here it is. So we also, I also was in communication with Jonathan Sundow from Princeton. Okay, so he's a mathematician I very much respect, and he was helping get the paper shaped up and presented in a way that is easy to understand from a variety of different fields of mathematics. Unfortunately, he passed away last winter, and this is really the weird thing with meeting people online is that all of a sudden the emails just go silent, and it's quite disturbing. I've had this happen a number of times. I once at the chemist, where all of a sudden later his daughter found his his computer, going through. He passed away, and no one knew, and so she went and reached out to all of those, and this happens. All right, so definitely pick up the phone and call people. Get a little more social, don't leave everything online. That's just a lesson I'm learning from all this. Because that happened with Jonathan Sundow after he was quiet for about a month or two. I'm like, all right, something's wrong. Something's wrong. And I went looking in the obituaries just because I've had this happen before. And sure enough, he had passed away. Very, very sad situation. However, he helped a lot. And hopefully he is in a better place of eternal truth. Good. Now, something on the brighter, or I should say darker side. All right, dark humor. I don't know if it's the brighter side, but when times are dark, it's good to look at humor, and especially if you're a mathematician. You don't want to only use your left side of the brain, right? You got to use creativity. If you're going to be coming up with new ways to solve important problems, you really need to be using both sides of your brain. And humor is just a great antioxidant. Okay, so you really got to keep that humor in your life, and whatever that humor may be. All right, I like Elvira. I was a big fan of her in the '80s growing up. And Elvira, about 4 days ago, at least 4 days before I started this video, it was announced that she has a memoir coming out, and you can order it. All right, I like this. I really want to promote it for you. If you like dark humor, or I don't know if this is really dark humor. Actually, it's dark and it's humor, but I don't know if it's dark humor. It's more like witty humor, snappy answers to stupid questions type of thing. All right, so. This video will help or this book hopefully will help illustrate how she came up with this character. She's the one that came up with, the phrase, "If I want your opinion, I'll beat it out of you." This woman in curlers in this movie is coming up and just really ragging on her. Say, "You don't fit in here. You barely fit into these clothes." And she just responds, "Listen, sister, if I want your opinion, I'll beat it out of you." And then the lady comes back, "Ah, never." And she just goes and attacks that. "Well, you never will," whatever. And so I'm interested in who comes up with this character, right? Well, what is the person behind that actually says, this is what I'm going to do. I'm going to have part of my costume is going to reveal all my bosom. I'll put a knife right under there. All right, so who? And this is the individual, Cassandra Peterson. And so if you don't know, when she was 1.5 years old, she was burnt in a kitchen accident and scarred over 35% of her body. And she says that she, was verbally attacked by the kids, and so had to constantly refine her witty responses. So if the kids are laughing at her, so I want the kids to laugh back at them and return it back on the attacker, and everyone laughs with me rather than at me. And it's kind of like the movie 8 Mile, where they're having these battles of wit, right? So it's not battles of violence, but battles of wit. Who could come up with the faster, funnier response in defense or in the attack? It's just, it's an art form, a comedic art form, of which Cassandra Peterson mastered, and she mastered it very early in life in order to, basically defend herself. And so if you think about it, all right, so if you have this weakness, all right, which you may at first perceive as a weakness, this can later become a strength if you are constantly refining your wit. Well, that so-called weakness, those scars in our life, well, they can help you to refine your strengths. And that's how that character came about. And I hope that in this memoir we can learn a little bit more about the psychology there. So if you look at her costume, what she has done is designed the costume around covering up all of the areas that were scarred and revealing pretty much everything else. All right, I think the whole thing is very interesting and fascinating. So I definitely like to check it out myself and recommend it. Even though I haven't read it, I definitely recommend it for you as well. All right. So now speaking of attacks, all right, let's attack some proofs. All right. So if you're going to go out there and say, I have a proof of the Riemann hypothesis, expect attacks, right? This is a necessary part of the process. Attacks at the person, not very meaningful. All right. So we're going to show where to attack a proof. And the three culprits are going to be Carroll, Brown, and Atiyah. Now, each of these three have a little bit of a cult proof. Okay, so no one in their day, I'm not sure about Atiyah, I'm not sure about any of them actually. Not that I can see really anyone clearly pointed out their error. So that leaves it hanging. They leave the world, hopefully, again, in a place of eternal truth where they now know their error. And if we can channel that eternal truth back into this conversation here, and we're going to go point out their error. All right, and I'm going to show you how I would do it, or how maybe even Hilbert would do it. We're going to go over this. All right, we want to go and we want to attack the proof. Why? It's absolutely essential. For making sure that we don't build theorems off of something that later turns out to be false. Okay, so we want math to be eternal. We want an eternal marriage between the proof and the hypothesis or the unsolved problem. And so that's what we're going to do. Now, in the last video, we ended with this operation. It's the last part of the paper, and it's the only thing that's kind of difficult to calculate. Your software packages out there can handle this no problem. But we went over this, and I'm not going to get into too much, but I like to summarize a little bit what I did in the last video, and because some have asked about this one. All right, so this is an operation, and so it has a couple conditionals. We have a squared there equals b, that's conditional. B squared equals 1, that's conditional. And then we have these equalities here. So when the real part of little s is equal to this, and the real part of big S is equal to this, let's solve for all the cases where the real part of little s plus the real part of big S equals 1. And with that operation, you'll find that there are no real solutions. All right? Are there any complex solutions? Let's just ignore the fact that we say imaginary and real part, and let's just say x and y. Okay, yes, there is one complex solution, but no real solution. And that's what we're looking for. And from that, we can say a lot about the symmetry of any hypothetical zeros off the critical line. We can say a lot about upsilon when it's not equal to 0, upsilon when it is equal to 0. And we can determine, as you'll see in the video right before this, you can prove the Riemann hypothesis in this way. All right, so all of the non-trivial zeros of the Riemann zeta function have a real part 1/2. Okay, the next video, we're going to present all the counter arguments that we've been collecting of others and how we handle it. See if they refute the proof, if they stand up to our defense, and go over that. Let's first show how to attack and why. All right. Oh, I forgot about this slide. So sorry. Again, this is not scripted. This is something fast for that last operation. Well, how do we solve it? Okay, so I know I plug this into the computer, but what's the computer doing? I did create a method, put up a method at ResearchGate. If you do a search from your favorite search engine, you should, maybe like Jeff Cook, Riemann hypothesis equation 8, should come up pretty quick. Now, you do need to be a published researcher to join ResearchGate, but you do not need to be one to download this file or the paper. So the paper itself for this direct proof of the Riemann hypothesis is also easy to search, and it comes up in this case right below it. All right, so you see there's a search. All right, so there's many ways you can perform that last operation. Okay, there's several different ways to do it. I present one method, okay? And because there's multiple ways to do it, there's really no reason to put it into the paper, okay? If a calculator can do it, it's pretty much easy to do. It's possible. All right, but I did put up there to show how here's one way to do it. Okay, so I mentioned about marrying a proof to a hypothesis, okay? So it's going to stand the test of time, all right? So the proof must carry the hypothesis across several bridges. And these bridges are the premises, okay? So you got this valley below, and we are trying to get to the other side. We need to get to the other side first, and then show others how we did it so that they can follow. All right, so it has to be clear instructions, not some general vague map, but a very clear, precise, step-by-step procedure to follow. And those bridges can be thought of as, or premises can be thought of as bridges in that way. So here's the real, in my opinion, the key way to attack a proof. Observe what it must accomplish and challenge that. All right, so I wouldn't look at so much at, and I'm going to get into this, I wouldn't look so much at, an equation that may be wrong, but really is not what we're trying to prove. I might take a note of it. It's a clue. I might say something about where the paper's going. But typically, you're going to read over everything and find the important parts of the proof and say, well, it's trying to accomplish this, and let's go challenge how they do that. All right. So that can be broken up into a couple different ways. The main issue is one wants to ask is there any ambiguity? As ambiguity is the antithesis of proof. Okay, it's the polar opposite. All right, and why is this the case? Because only math is certain. Are your finances certain? Are your relationships certain? Are your beliefs certain? Or are we? Only math is certain, and because it's certain, we don't want to be building off of something that is just simply accepted, even though it's nonsense. We like the fact that at least math is certain in the world. Okay, and that comes from Descartes, the philosopher and mathematician. So another part of observing what a proof must accomplish and challenge that would be, are the definitions properly presented? We don't want any circular arguments. We don't want any circular definitions. What is a circular definition? So if I say we're going to add 3 coins to 5 coins, okay, well, what's your definition of a coin? Well, it's a metallic disc-like object that has some value. Okay, so what's a disc? Well, it's like a coin. All right, that's a circular definition. We're going back to describe the thing. And you guys probably know all of this, and that's okay. But just want to clarify, we don't want any circular arguments that you can't, nor circular definitions. You're not going to be able to prove anything from them. Okay. Now, are the premises clearly presented and falsifiable? We spoke about the bridges, right? All right, so are the bridges clearly presented? Is it vague? Is it and then is it falsifiable? If we're talking, well, you have to go all the way out to infinity. When you get there and turn around and come all the way back, you'll get it. Well, that's not falsifiable because I can't get all the way out to infinity. So there are ways of proving infinities, like all of these that are moving in the direction here are going towards infinity. All those move in the direction here. We could put them into different groups, which is kind of what the proof, this proof, it does in a way. All right, but let's talk about premises, because this is where so many proofs fail. Now, ambiguity, this happens with a lot. I wouldn't say it happens a lot with from mathematicians with a lot of experience. It does happen a lot with mathematicians who not as well prepared. All right, so I don't see it that often. None of these three proofs really kind of fall into that area. Not exactly. All right. So, but premises. This is a big thing. All right. Right. These are the bridges that we're carrying the hypothesis across. All right. Now, are they falsifiable? Is it something we can prove with the information given? All right. Let's kind of get into the first proof. All right. And we're going to take this Hilbert method and apply it to it. All right. Hilbert. All right. So he had his own millennial prizes. So people are talking a lot in the comments a lot about the millennial prizes with the Riemann hypothesis. All right, so Hilbert had 10 unsolved problems that he thought were the most important to get to, and only one correlates to the millennial prizes, and that is the Riemann hypothesis. Now, I heard this from somebody else who heard it from somebody else, so we don't know if it's true, but it is alleged that Hilbert had this little form that he would give his students in reviewing papers. All right, and it would be, dear blank, your first error is on page blank, line blank, and then leave a little space with a little information they want to add. And I put this second part here because I think it's equally as appropriate. If you could fix this error, I would be happy to take a second look. With respect. All right, that's the nice way. You give this to your friends. Say, yeah, I see your error here. Go fix that. Come back and I'll take a second look. Okay? And so I'm going to apply this to each of these three individuals. And it's funny because the individual who presented this, shared this with me, he spoke of it as though this would be an insultive, disrespectful way. I disagree. As a mathematician, I respect this. Tell me where the error is so I can go look at it. Be specific, not just throw your hands up and walk away. That's disrespectful. All right. So I'm not going to look at it. It's nonsense. That's disrespectful. All right. And that leads to potential cult proofs. All right. So and like these three we're going to talk about, leaves people hanging. They don't know, so they don't keep working on these unsolved problems because they believe that they were solved 100 years ago, which was incorrect. All right, so this is the importance here. All right, in my opinion. Okay, so you may disagree. I like the Hilbert method. I think we're going to use it. All right, we're going to talk about a simple proof of Fermat's last theorem. All right, so yes, this is about the Riemann hypothesis, but there's a lot of crossover. Both are about infinities, okay? So are all of the non-trivial zeros all the way up to infinity have real part 1/2? And then the Fermat's theorem is, are there any rational solutions in this equation, which I'm going to show you, out into infinity? Okay, so it's similar. But here's the big problem with it. This is not a mathematical problem. This is a psychological problem, okay? And both Fermat's last theorem and the modularity theorem and the Riemann hypothesis were almost universally considered inaccessible to proof by contemporaneous mathematicians, meaning that they believed them to be impossible to prove using current knowledge. All right. Now, if you're a student or a lay math enthusiast and you see this word here, what's that word? Okay. This should not be put in the same sentence with math or mathematician. So you see some interview where they're asking a mathematician, do you believe that the Riemann hypothesis is correct? Ignore everything they say after that. It's meaningless. It is either correct or incorrect. And I really wish mathematicians would stop using this word, but I understand that everyone likes to know. Everyone likes to know. Or if somebody asks their beliefs, so, yeah, I'd love to share my beliefs. Who wouldn't love to share their beliefs, right? This is a problem in math, okay? And the second big problem is right here, this word right here. What's that word? Okay. almost always, just like these two theorems, they're always wrong. They're always wrong when they do this. So it's just really something we got to get past. All right, stop combining these in mathematics. We want math to be certain. We don't care what anyone believes. Okay, it doesn't matter. All right, we only care is or is not. All right? So if we want to leave some ambiguity, go have a political debate. All right, so I don't care about any of that. All right, good. This simple proof of Fermat's last theorem, is by Carroll. All right, who is he? Lewis Carroll. It's actually his pen name. Okay, so he was the author of Alice in Wonderland, or Alice's Adventures in Wonderland, and Through the Looking Glass, the sequel. Okay, but I respect him because he was using both sides of his brain, mathematician and a fiction writer. All right, I think this is very important. All right, he's using both sides of the brain, and he was a skilled mathematician. He was not an amateur. Doesn't mean he was right. All right, no mathematician is always right. Is it okay to make mistakes? Of course. All right, of course. Is it important that we learn from our mistakes? Yes. Is it important that we admit and correct our mistakes after somebody finds them? Yes. I have found I used to go over. Back in the early days, I used to go over other people's Riemann hypothesis proofs. All right, and when I'd find an error, I'd contact the writer, and one I contacted I still find it hard to believe. I said, "Oh, your error, you got this error here," and then pointed out, and he'd be like, "Oh, yeah, it is." But I already sent it off to the publisher, so not much I can do about it now. I'm like, retract it. Write a letter, note to the editor. You can't let it go. If it's okay to make mistakes, but you can't just kind of allow it to kind of go through into the system and get out there and confuse everyone. All right, let's go to him. All right, so he lived, in the 1800s. All right, so this proof is from a long time ago. All right. Looking at this, all right, I circled the area. We're going to zoom in on that. All right. If you're not familiar with Fermat's last theorem, first thing to note, I don't know why it shouldn't be called a last theorem, because no one knows that he actually even proved it back in the day. It should be more called something like Fermat, the legend of Fermat's lost theorem, or something like that. But it is a theorem now, all right. But a theorem is something that has been proven, all right. It's already proven, so I never really got that one. Doesn't matter. Okay, so the theorem asks this question. Given x to the power of n plus y to the power of n equals z to the power of n, are there any rational solutions for x, y, and z for n greater than 2? All right. So we open up. That's the question the unsolved problem asked. All right. So Carroll comes here. All right, and I'm just going to read it here. In case n equals 2, so he's talking about the cases where there are known rational solutions. In case n equals 2, we have x squared plus y squared equals z squared, which is obviously the equation of a right triangle. Dead air. Note my silence, because this would be one of those things we'd want to think about. Is this obviously the equation of a right triangle? It's not obvious to me, but let's continue. All right. His argument and conclusion is based on that premise. Now, is there any way to stretch the math later to make what he found to be accurate? We're going to see. All right, let's just see it, because let's see how his proof follows. All right, we're talking, is there any ambiguity? Are there any errors? Are there any false premises? All right, so he says that x squared plus y squared equals z squared represents a triangle and must represent a right triangle. And let's just fulfill his outline. We're going to lay out an outline of how he goes with this proof. All right, these are his quotes. Okay, so we observe that no cross product terms in x and y exist. These are things coming out of his proof. Because the sum of any two quantities x, y, and z is greater than the third, we then conclude that x cubed plus y cubed equals z cubed represents a triangle. Then we conclude that if x cubed plus y cubed equals z cubed represents a triangle, it must represent a right triangle. And since we have shown that the triangle represented in the Fermat equation is a right triangle, then we must have that no three positive integers x, y, and z satisfy the equation xn plus yn to the power of n equals z to the power of n for any integer value of n greater than 2. Okay, so that's the outline of his proof. There's some things he does in between there, but that's the outline. Okay, so there's only one little problem here. It's not a triangle. Okay, it's an infinite cone. All right, so what he sees as triangle is if you take this infinite cone, put it in a box, we're then making it a finite cone, and then we're going to take the plane section, which is like an infinitesimally small sliver of this, cross section of this, and then cut it in half right here, and then cut it in half right here, and we get this right triangle right here. That's what he sees in that equation. And let's see what happens with that. Now, well, see, because I know a lot about double-sided cones or plane sections of infinite cones. All right, if you've seen the third video, you may remember this diagram. All right, well, you don't see it there because we have the zeta function constrained to the tangent half angle formula. But if you remove that and just show it one term by term of the equation that we presented in the proof, the first term was 1 divided by s minus 1. All right, so we take out zeta function of this and just lock that in. Well, then you can see the plane section of a double-sided cone. All right, so we had a plus b, all right, the paper. All right, so a was 1 divided by s minus 1. It's right there in this point. And that plane section of a double-sided cone is internally tangent to the inverse of the imaginary part of s, and externally tangent to the 1 divided by s minus 1. So I know a lot about it. Now you don't see it right there. You see that right there? Okay, so that's plane section of a double-sided cone. And since we could give any s, we could probably stretch that out to infinity as well. All right, and rotate it and spin it. We get the infinite cone. All right. In fact, Greg and I actually used this plane section of a double-sided cone in a single statement solution for the complex argument. So I know a little bit about it. Now, what? All right. What happens if we don't consider all the rotations of that right triangle? Then we get this. All right, so x squared plus y squared equals z squared does not represent a triangle anymore. It doesn't. And therefore it cannot represent a right triangle. And therefore we cannot conclude that x cubed plus y cubed equals z cubed also represents a triangle. And we can't much less consider it a right triangle. And since we have not shown that the triangle is a triangle representing the Fermat equation, we can't conclude the theorem. All right, we can't conclude anything from that because we are working from a false premise. All right, given a false premise, x divided by 0 equals 5. Can we prove anything from this? No, because it is a false premise. Okay. All right, so we would write back Carroll. So, dear Carroll, your first error is on page 1, line 26, not a triangle. If you can fix this error, I would be happy to take a second look. With respect to J.N. Cook. And this is the respectful thing to do. Point out the error, find it, clear. You don't need to go into a whole lot of detail. Don't talk about his personality. Just not a triangle. I mean, we just discussed it, so we understand what that means, but we could explain it a little bit. That's basically what we're going to do. All right? So we got to make sure that the premises are clearly presented and falsifiable. Well, his were clearly presented and falsifiable. It's just that the premise was false. Now, sometimes the equations are false. All right. This, I think, is probably one of the most common things because who hasn't left out a variable? Who hasn't had an error? Especially when you get proofs that are like 100-page long, like Wiles. I mean, man, can you imagine the tedious amount of work to go over all of that? All right, because any one of those equations could be wrong. They're usually easy fixes. All right, if the individual has planned and understands and really knows the proof very well, like the back of their hand, usually a typo's easy fix. So that's why it's important to look into them, and maybe we can point them out. Maybe they can go back and fix it. So this next one is one of those cases. Okay, it's George Spencer Brown. I think he's the most interesting looking mathematician of all time. But he's an author of Laws of Form, and he's also, I don't know how well respected he is in the math community. I do know that he has another proof out there on the four-color theorem, which no mathematicians have defended, but at least one has said it's worth looking into. All right, so definitely he knows his math. All right. Now, lacking a better way to say that. He does know how to use a calculator. All right. So look, here's the thing. All right. So again, is it okay to make mistakes? Yes. Do we try to learn from them? Do we try to correct them? Yes. All right. I don't know that anyone brought these things up to him in his lifetime, and it probably should have been done. But maybe his friends didn't know a lot about math. I don't know. All right. But this first, when I'm coming here now, I know a bit about the Riemann hypothesis, and if I'm a native English speaker and somebody comes up to me speaking with a dialect, I know within the first sentence or two, hey, they're not from around here, and this is the same way with the Riemann hypothesis, and so when I see this first sentence, I immediately can see that he's speaking a little bit with an accent. Okay, so I know what he's saying. I know what he's saying. Not technically the correct way I would say it, or that if native speakers would say it, but I understand the point. He reads the Riemann's hypothesis, notably that the complex zeros of, and it gives this inequality. The problem is this the equality does not hold for any other values with the real part less than 1. So all you needed to do is put like a little bit of a comma, real part of s greater than 1 here, and that would be true. Because in fact, on the right-hand side of this, there are no complex zeros. All right, so it's a little awkward, not a big deal. I wouldn't set the paper aside for this, but it just is one of those things you look at and okay. But again, that is not a showstopper or anything like that is, okay, because that's not where the proof's not trying to accomplish that. All right, so what is the proof trying to accomplish? Well, he gets it up pretty quick. He's going after Littlewood's result. So Littlewood's result is that the prime counting function is asymptotically equivalent to the logarithmic integral. All right, and so this has been shown to be it implies the Riemann hypothesis. All right, and so if you can prove, find what the error term is there, and how, how do I explain? All right, so it's a big O function, and it's a very dark jungle, which I think has no hope of coming out of alive. It's something that I looked into the early years of the Riemann hypothesis, and its equivalence would be of trying to find the error terms of these, trying to find the meaning would be like equivalence of the Basel problem multiplied by infinity. Okay, a very, very difficult way to go about proving the Riemann hypothesis, but it's also one of probably the first steps somebody attempts at the. If you have this important finding, yeah, you want to go explore it, but it doesn't easily, lay anything out. It doesn't make the situation clear that I've found. All right, but he's going to go in that direction. All right, he's going to start his first premise is that he's going to prove. And remember when somebody says obviously or clearly you can see, or like in the last one, that would be one of those things you want to think about. So this is another one. I shall in fact prove. That would be one of those things you want to think about. All right. The absolute value of the prime counting function of n minus the logarithmic integral of n is less than the absolute value of the logarithmic integral of n to the power of 1/2. All right. For all n greater than 1. All right, and then he goes on how that's more than enough to prove his proof. Wow, okay, well, I'm going to go and plug in. First thing I see here is I'm going to go plug some values in for n. Let's just get on the same page and see if that's even close to being true. You let n equal 1,000. Okay, that's true. It's the first try. Well, let's just add a few more zeros. Let's just say n equals 1,000,000. And we start to see the problem when you go out towards infinity, even the direction of infinity. All right, so the left-hand side is equal to 3.06296 times 10 to the power of 6. All right, the right-hand side is a bit lower than that, 280.40604. I would say that the left-hand side is greater than the right-hand side. Yeah, so not really any way to stretch that because that's the first premise he builds on, and he says he's going to prove that it's greater than the left hand is less than the right hand side for every n greater than 1. All right. So in this case, it's not. So by finding a counterexample right off the bat, the premise is gone. We can't go any further with that, since he says that premise is required for the Riemann hypothesis to be correct. Well, then his proof is incorrect. All right. So sometimes the math is wrong and very easy to check. So I think it's very important to just grab a calculator, piece of paper, and pen, and just start plugging in some values for these claims and these equations. Anything somebody's going to present. Okay, so we would write Dr. Brown, or I don't know if it's Brown. We write him a letter. Say your first error is on page 1, line 11, n equals 1 million. And he would understand, if he understands his paper and what he's written, he would look at it and go, oh, crap. And then I would leave it, if you could fix this, I'll be happy to take another look. Well, this is what his friends and colleagues, probably should have done in his lifetime. Just because I would like to see if he could come back with another proof. That would be an impressive result. Like I said, that Littlewood result, exciting, very, very difficult to prove. All right. Now, one final example. And this is a combination of a circular argument and a false premise. Okay, this happens a lot with proof by contradiction. It's a common mistake, I'd say, by proof by contradiction, because sometimes the author can get confused, sometimes the reader get confused, and just go nowhere. I mean, we're supposed to be carrying the hypothesis across bridges, and everyone should easily follow. I'm not a big fan of proof by contradiction, but it can be used to solve some very important problems. Some very difficult and some very easy but important problems. All right, so this is Atiyah's Riemann hypothesis proof, and it came out a couple years ago. If you haven't heard of those other two proofs, you almost certainly have heard of this because it just recently happened. And a lot of what I said about the other two, friends and colleagues, okay, I wouldn't say what the other mathematicians did with Atiyah's proof was reprehensible, but I would definitely say, I think we all could agree it could have been handled a little better. And where could it have been handled better? Well, sit down with a pen and paper instead of focusing on the fact that he bypassed everyone's opinion to just go out there and announce the proof. Why don't you just go ahead and present the once it's out there. I mean, once it's out there and it's in public domain, well, then we have to go and point out publicly where the error is. And if that's what he wanted, that's okay. I'm happy with that with this proof that we have. That's why I'm new to it. I'm not concerned about that. I also don't have the qualifications that Atiyah had, so I don't have as much to lose with a false premise or false statement if it's to be found. But that's what you should have done, is just go, well, like I said, hindsight is 20/20, so it's okay. But I would like that any proof out there, especially from some gentleman with this guy's credentials, all right, go find the error, point it out, give it to him. He passed away like a year and a half after he came out with this. That's plenty of time to people to find an error. I think this took me about 8 to 10 hours of work to find out multiple errors. And if you found multiple errors, just point out to him and have him go fix it. But I don't know his personality. Maybe he was very defensive and wouldn't retract anything he said, and that maybe that was the case. I don't know. But look at these awards. Holy smokes. All right. Look, he's a heavy hitter. All right. So one may ask, does he really need to be going and proving the Riemann hypothesis after all of these awards? And I say, yes. Yes, he does. He who dies with the most prizes wins. All right. Sorry, not really. So you can buy the collection of all of his works. They got a little encyclopedia, I guess, almost of his entire works. You can do that. He's quite an accomplished mathematician. All right. So, like I said, everyone can make a mistake. All right. Do we learn from the mistake? Can we fix the mistake? Good. One area I would like to say right off the bat is Atiyah's proof is not ambiguous and vague as many have said. Okay, it's not. Just because you don't understand the proof doesn't mean it's vague. Right? So there's a big difference between those two. I'm also going to show that it is falsifiable. So these are some of the discussions I saw out there. It's not falsifiable. Now, if he kept moving the goalposts, so that's kind of an example of being falsifiable. But the paper itself, as it stands, as I could read, it's falsifiable. It's very easy to go through that. All right. Okay. Now, it does contain a false premise. So if you accept that false premise, then I can see how it would look very vague and ambiguous. It's like, this doesn't make sense. Well, no, it's a false premise. Of course it doesn't make sense. It invalidates the proof. Let's go into it, all right? So he references back to a paper he speaks of something called a Todd function. I'm going to get into that in detail. And he references back to a paper where he claims that he used the Todd function and the zeta function in order to find the fine structure constant's value to a very high precision. I think that's beautiful because I'm fascinated by the fine structure constant. I'm excited about it. It's one of those values in physics where it looks like it's probably too small to be a geometric constant, but also too big to be anything physical. Well, we know it's not a physical constant now, but it's big enough, too big to kind of brush aside in contrast to the size of the electron radius and electron charge. It's a very big number compared to those. What is it? No one knows. Okay, that's why I'm very excited about this paper, and I get there. I'm like, okay, well, this is cool, even more interesting than the proof. But let's go look into it. All right, he's got a couple of new symbols he's introducing, and I don't have a problem with that. There's only so many letters in our alphabet and in the Greek alphabet, and we're running out of things to symbolize variables. Good, go grab some other ones. I think this is bound to happen, and nothing wrong with that. Okay, I don't exactly know what to call them. All right, so I'm just going to call it the reciprocal of the fine structure constant and upside down h. I don't know what else to call it. All right, so we have this equality where we have the upside down h over the Euler-Mascheroni constant is equal to the reciprocal of the fine structure constant over pi. Okay, and that's kind of interesting if you got something else to show for it, because all three of those values, with the exception of upside down h, we know those are known constants, and so we can then easily, with a little algebra, determine upside down h's value, and its value would be this, 25.1781, so on and so forth. But he does actually say he has a way of calculating upside down h. I'm like, there it is. All right, let's get to it. He's gonna nail this. And so we have the limit of convergent series, and we can easily go and get the value. Just one little problem. It doesn't equal 25.187 or whatever. Now, maybe I forgot a 2, all right? Maybe he forgot a 2. Maybe he forgot a variable. I don't know, but I know that is not giving me the same value as the other. And I think what has happened here is he simply, there's a typo in there. That's it. There's a typo. No, you don't need to read it any further. It's a typo. And this happens often. So many times with me, it's like find the algebraic cure for cancer and delete the file. And I'm like, I lose so many things. All right, so it happens. Well, not much you could do with that at this point. I'm sorry, there's no point going on. So I'm not interested in that paper any further because the whole point of it is finding the precise value of that. Now that's fine. So I'm gonna go back to the proof. And fortunately, there is enough to know about mentioned in the Todd function in the proof itself that I can actually you could extract all the information out of where he's going with this. Okay, so there's a handful of different properties of this so-called Todd function. One is that it's polynomial. It's also a real value, but these are the three properties that I'm interested in, and we're going to come back to those in a little bit. All right, so this is his outline. We're going through the outline, all right, that I put together here, just like I did for the other ones. All right, and then he's got this operation over A that's going to produce this this closed rectangle within the critical strip. Now, you know me, if you see the last videos, this is it, right? Now you're talking the right language. All right, so everything he's doing so far is he's moving in the right direction of the Riemann hypothesis. We're gonna create this closed rectangle, and we're gonna prove to see whether it's possible or impossible to exist. Okay, and from this we get the degree from this operation, from this closed triangle. We can get the degree of the polynomial that the Todd function is. All right, so that's cool. All right, now we're going to letting a equal b, where b is a non-critical, non-trivial zero of zeta function. And we're going to go over all of this. It's just the outline. Consider f of s equal to the Todd function of 1 plus zeta of s plus b, all minus 1. All right, so that's where he's going to go at. We're going to get into that. Since f is analytic at s equals 0 and f of 0 equals 0, letting f equals g, which are these functions here, f and then g, equal to f, one gets that f of s equals 2 times f of s. And since complex numbers are not characteristic 2, this simply means that, well, if fs is equal to 2fs, it means fs is 0, right? Such that the Todd function minus 1 equals 0. Cool? All right. This implies that the zeta function of s, which is s equals 0, is 0, which is false, and therefore we get a contradiction. No b's can exist. Therefore, the Riemann hypothesis is correct. That is his outline in a nutshell. Let's tear into it. In understanding the Todd function, it helps to compare it to a function that you may be familiar with. All right, so let's compare it with the prime counting function, and we're going to play around with it. And sometimes the best way to get any understanding of a function, a new function, is just play around and give it some values, see how it behaves. We know its properties. Let's just go compare it. So let's compare the first property with the prime counting function. Now you remember he's taking the Todd function of something minus 1 and he's setting it equal to something else. Okay, so we could do the same thing with the prime counting function. All right, and setting it equal to Riemann's final result, which has the non-trivial zeros in it. All right, so the right hand side it gives you the number of primes less than x. The prime counting function gives you the number of primes equal to x. So prime counting function of 7 will give you 4 primes. The right-hand side of this will give you 3. Or not prime, not primes, 4 primes. Yes, there are 4 primes, so the value output is 4. All right, so with up to 7, you got 2, 3, 5, and 7. All of those are counted on the left-hand side. You simply subtract 1 and you get the right-hand side. All right, so we're going to then try to use that to extract the non-trivial zeros out of it. You see where they are? Those non-trivial zeros? We discussed this in the past ones. So is there a way to do this right here? Set the Todd function of s minus 1. Set it equal to the right-hand side of Riemann's result. All right, so there's a way to do it. Or is there? That's what we're going to find out. All right, so we can do the Todd function of 1 plus the zeta function. Now, so we have the zeta function on the left-hand side and the non-trivial zeros of the zeta function on the right-hand side. Can we get any information? Now, remember b, according to his paper, the outline, b is a non-trivial, non-critical zero. So it's a non-trivial zero off the critical line. These row are all the non-trivial zeros on or off the critical line. So we now are actually separating the meat from the potatoes, I guess you could say. All right. So, and he puts these little these braces because the Todd function itself is the 1 plus the zeta function. So if zeta of s plus a non-trivial 0 would go to 0 at s equals 0, 1 plus 0 equals what? Right? 1 minus 1 equals what? 0. But I don't know. Does that work with s equal to 0? We'll come back to that and see. All right. So Riemann, I think he denoted this final result little f of s. All right. So with Atiyah, he's going to talk about big S. All right, this little fs means something else. All right, let's look at the first property, see how it compares with the prime counting function. So we're going to better understand the Todd function from this. All right, so let's let the prime counting function have this equality. What values does this work for? Well, it is true for all s when g of s equals 0 or f of s equals 0. So if later we're going to set f equal to g equal to f, well, they're all equal to 0, it's going to work. All right, good. So the prime counting function works in this way for all values of g of s equal to 0 or f of s equal to 0. So let's apply the property of Todd function to the prime counting function of the second property, which is this. Prime counting function of square root of s equals the square root of prime counting function of s. What values is this true for? It's true for this really neat sequence, 0, 1, 9, 10, 25, 28. I like that so much, and it's not literature. I looked it up. So I'm going to call it the Jeff Todd sequence. Or maybe just the Jeff sequence, because I really don't know who Todd is. And he didn't come up with it. Just kidding. All right, so comparing the prime counting function and the Todd function, we get that it is true for, they share these values, or the values it is true for. So if s equals 0, it is true they link in, and if they're 1, they link in, and it kind of separates a little bit, after that, but maybe there's some way to tie those together. Let's look at the third property before we even attempt that. All right, let's apply this property of the Todd function to the prime counting function and see. Square root of pi, I'm going to say it out. The prime counting function, okay, sorry, I need to take a break. Square root of the prime counting function of 1 plus s is equal to the prime counting function of 1 plus s divided by 2. What arguments is this true for? Well, we lose all of my whole sequence. So this is pretty much where we separate from the Todd function, except that we have it's true for argument s equals 0. So since all of the other properties work for s equals 0, we are in good shape. Now what we're trying to do with this Todd function is right here. All right, now we're learning about Todd function. We're trying to get familiar with it. All right, does this work? All right, we let s go equal to 0. Can we extract the non-trivial zeros out with this value? All right. Well, unfortunately, the third term does not converge. I don't know how to get it to converge. All right. If this were a true statement, it would have to be equal to log of 2, but I really don't know how to prove that. All right, because the first term goes to 0 and at 0, and the second term goes to 0, but I don't really know how to do that. So I'm not going to try it, which is probably why it's not in the paper. All right, this is just me trying to get familiar with the Todd function, and a good way for you to, when you go in and look at somebody else's paper, you're not familiar with something, just go compare it to something you do know and see if you can extract the information out of it. All right, because we get back to this issue. This is the point of his paper. He's saying f is analytic s equals 0, so that's the one value he's going to look at, and f of 0 equals 0. Now we're going to take f equals 0 equals f and deduce the identity, and we're going to come out with some information about that. All right, that's the end of his proof right there. He gets there, and so that's reading through the paper, skipping through it. Now we have to go back to the premises, and we know where he's going with this. We understand the Todd function now a bit, and we're to go and just see if we can get to draw the same conclusions, if we can get as far across the bridges as he alleged he did. All right, let's go to the closed rectangle. All right. I love closed rectangles within the critical strip, so let's just go and hammer around that. All right. Hey, look, I put a closed rectangle inside a closed rectangle. Yeah, anyway. Okay, let's unpack the less than case. All right, so we have an inequality less than or equal to. All right, let's just look at these solutions. All right. Before we do so, I don't like the way he has the real part of s minus 1/2. We can just say it's real part of s minus 1/2. I don't know. Just for me, I like it better that way. Not a big deal. All right. What is this saying about a? All right. If you don't know, what does it say about a? We need to know what a is because it's going to be, that's the operation is taken over a. What does it say? This right here, this statement, the absolute value of the imaginary part of s is less than a, means that a is a positive real number. Okay, so we got some information about a now. And why? Because inequalities are not well defined in the complex plane. The field of complex numbers is not totally ordered. Okay, so the general solution then for this, all of the real parts of s are going to be where? Within the region between 1/4 and 3/4. All right, so just about halfway inside the critical strip. So 1/4 is the halfway point between 0 and 1/2, and the 3/4 is halfway between 1/2 and 1. All right, what is he doing here? All right, well, he's going to take s, and it's going to be anchor point to these non-trivial zeros. All right, so let's keep reading though, but that's what I'm going to do. I'm going to go into that a little bit more. All right, this right here, as you know, does not limit the solution to the entire critical strip. All right, so the anchor points S are not going to be within the entire critical strip. They're going to be here, and all these B's are going to be non-trivial zeros outside. Oh, they may be here. Right here, I have them on the line, but they could be outside or whatever. But they have to be within the critical strip. All the non-trivial zeros have to be within the critical strip. S, the anchor points, do not necessarily need to be, or at least so he's saying. All right. So I'm not really sure what he's doing that. I think I like the idea of him just saying less than 1/2, and then we got the whole critical strip. But it's not my paper, and I don't know where he's going. So I'm assuming there's a reason he does this. So we continue. All right, we're going to unpack the equal case. All right, we have less than or equal to. What are the solutions when it is equal? All right, so when A is equal to the absolute value of the imaginary part of S. Well, for A equals 0, which is one of the solutions, or one of the general solutions, we get two possibilities of what S could be. It could be a real 1/4 or a real 3/4. Okay, those are both solutions for when A equals 0. All right, for when A is greater than 0, which is all the other real values. All right, we get 4 solutions. So we got to talk about points on a rectangle, right? So we got 4 different solutions, just as we did with the non-trivial zeros in the last thing. All right, now, I don't know if actually Atiyah came and even opened up these solutions. All right, I don't know. I'm assuming he knew there was 4 points on the rectangle, but let's just see where we're going. All right, these are the 4 solutions. All right, this is not hard to calculate. All right, it's plus or minus 1/4 times I times 4A plus or minus 3I or 1I. All of those 4 are one of the possible solutions for all A greater than 0. Okay, so now we have information. And that's what I do when I go look over somebody else's proof. I'm going to take the premise and I'm going to throw some values in it. I'm going to find all the solutions, like you saw with Spencer's proof. I'm just going to plug in some values to see if it's true. Spencer Brown, I should say. Okay, so let's go follow his steps. We get into the proof. Now I know a lot about the triangle. I know what all its solutions are, all its possible solutions. Or not triangle, rectangle. Still thinking out Carroll. All right. The rectangle, not triangle. Let's see how he goes about the proof. All right. Assume there's a 0, B, inside the critical strip, but off the critical line. Okay, non-critical, non-trivial 0. All right. Given B, take A equals B in 2.1. No. 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 You cannot do that. You cannot set a real number equal to a complex number. All right? The non-trivial zeros are absolutely all complex values. How are you going to do that? That is a big problem. So I think maybe he's considering it something else. But right there, no, that's what he means. Zeta of B equals 0. Oh boy. Okay, that's a problem. You can't do that, and I'm going to show you where it is. All right? This is not. We're not going to end it here. Don't get excited. Think this is the whole thing. It's not. It must be a typo. It must be a typo, and I think it is. Let's go ahead and see what, though. If it wasn't a typo, this is what it would mean. It would mean that the complex number is a positive real number. If you're setting it equal to a positive real number, then it's a positive real number as well. And inequalities are not well defined on the complex plane, so it must be a positive real number. But it has already been proven that there are no positive real zeros, B, for the zeta functions, so one cannot assume it to be true. It's a false premise as written. All right, one cannot assume something to be true that has already been proven to be true in order to prove something else false. Now, I discussed this example earlier. Given x divided by 0 equal to 5, which is a false statement, prove that 2 plus 2 equals 5 is also false. All right, you can't do that. All right? You can't take something that is known to be false and prove something true or false from it. I don't care if the right-hand side is false. You can't prove anything at all from the left side. All right, given a false premise, you cannot prove anything further. All right, it's done, dead in the water. Now, in some debates, political or whatever, religious, whatever, anything non-mathematical debate, there's sometimes people use snuck premises. And a snuck premise would be where something usually involves the word obviously or clearly or something like that, and they put their little snuck premise in there, which is, well, we didn't prove that premise in the first place, but you're using it to prove something. Because of this, you get this. All right, in math, it absolutely has to be proven. It has to be a correct premise. Now, I'm not saying this is a snuck premise. It's not. In math, it's usually just a false premise. It's a mistake, right? All right. Now, if somebody intentionally has a proof where they're using x divided by 0 because 5 to prove something, then that would be a snuck premise. But if they actually are doing their best, working hard, it's just a false premise. They made a mistake. All right. Well, you cannot prove anything what's given. But this is where it breaks down. The outline breaks down from that. All right. You can't let A equal B, and therefore you can't say that B is a non-critical, non-trivial zeta function. Therefore, you cannot say anything about the Todd function of that because B's not a non-trivial 0, and you can't say that F is analytic at S equals 0 because you also have that such that the non-trivial 0 is there again, and you can't say anything about zeta of S equal to 0 because, well, I don't even know if S can be equal to 0 in this case. You can't prove anything from it. All right, you can't say anything about B, and you can't say anything about the Riemann hypothesis as written. So, this was the final result that I saw. You know, maybe he had this error and no one pointed it out to him. All right, this is what I would write back to him. I'd say, now look at him. He's looking at me like, really? How many rewards and prizes do you have? I say, well, yeah, really. Your first error is on page 3, line 13. A does not equal B when A is an element of real number and B is the element of the complex number. If you could fix this, I'd be happy to take a second look. And you know, he'd be like, okay, yes, it's a typo. I don't mean this. I don't mean it's equal to A equal to B. I mean absolute value of B. And I go, yeah, that would make a lot more sense. Okay, then we can go with this. What does this say? Now we're going to express B in terms of his real imaginary parts. All right, and that then puts it in this region. All right, let's consider the inequality, the less than. All right, this implies that all real parts of S are going to be within 1/4 and 3/4. Okay, so these are the anchor points. All right, why would he do these anchor points? All right. So if you know anything about Gaussian primes, they have a limited distance that they could be from any other complex number. And I don't remember the exact maximum distance they could be. It's something like square root of 1/2 or k divided by 2, square root of k divided by 2. But there's a maximum distance between Gaussian primes and any other complex plane. Okay, there's a maximum distance they can ever be away from. All right, and so you can then use that information to map from an unimportant S to a very important S, which is a non-trivial 0, or to be. Right, so you can use that for Gaussian primes, which is a more important number than any old average complex number, and you can use these relationships, you know, and I'm going to call anchor point because it's kind of like you can't detach from it. Once you tie these together, you're stuck with it. When we're going to tie this S to that B, we're stuck with it. All right, so we have this real part of all of these S's for any given complex non-trivial 0 off the critical line. He's going to say they're going to be in this region. All right, so remember that little strip area. So we're back here again. We're going to go a little further with the proof. It goes forward. If we allow that absolute value, we can move a little forward. All right, but then he says that S is equals 0. Well, and then we got into a problem. I went into a big problem because that's just a bit outside. If the real part of S is outside that area and all the possible solutions are within that area, how are we going to use it? It's undefined. All right, in that region. 0 is undefined in that region. We defined all of the real parts of S to be within that region. If it's outside that, it's not defined. Okay, so that's a bit outside. All right, so where does it break down if we consider that? Well, we can't say that F is analytic at S equals 0 because it's undefined. All right, it's not in that region. And we can't say that. We can't say anything about S of zeta of S equals 0. I didn't say it. To me, it looks like, if anything, it's undefined. Zeta of S equals 0 is undefined. In any case, we can't say anything from that for the same reasons before. It is a false premise. All right. So, you know, he's looking at me again like that. It's like, really? Well, this is what I would say. I would say, dear Atiyah, your first error is on page 3, line 17. 0 is less than 1/4. And yes, really. But that may not really be what he's meaning. All right, that's not really what he's meaning. And I suspect not, actually. He's come too far as a mathematician. That is not what he meant. And I didn't think it when I first looked at it. I don't know why he had this quarter then there. Maybe he meant this. Alright? Maybe he meant that it's less than or equal to 1/2. Now that gives all the real parts of S in the critical strip. Now we're getting somewhere. All right. Yes, when it's less than 0 is outside, but we have the equality, so that does put 0 on the line. Bingo! Now we're locked in. We got our anchor points. Okay, so we're going to consider S equals 0. And it's anchored there to some non-trivial 0 off the critical line. All right, and he says the analytic. But there's something I'm seeing in that too. There's something I'm seeing in that. Let's just use the calculator to see for sure if I'm right on this. Double check my math here, but there's something I see funny when we let them equal to it, and it is that yes, B equals 0 when S equals 0. Ooh, just like the problem was setting the prime counting function minus 1 to Riemann's thing at 0, considering that 0 there, funny things happen with 0. I mean, you run into the undefined things, but there's also not all zeros are alike, as you learned from the other videos. Some are trivial, some are non-trivial. All right, anything multiplied by 0 is 0. You're always, I mean, obviously, it's an important number, but it can be tricky. All right, these are all of the solutions. All right, whenever S is equal to 0 or 1, both those anchor points, B is going to be equal to 0. Well, that's not a potential non-trivial 0. All right, B equals 0 is not a 0 zeta function. All right, that again is a false premise because it says right here, B is a non-critical non-trivial 0. Well, if B is 0, that's not a non-trivial 0 then, and that's the premise. Right, that's the premise. It's not the final result. That's the premise. We're building off that. So we can't. I don't really care if F is analytic. It's certainly not analytic at S equals 0 because it's undefined or it's 0. We can't say anything at the right-hand side of this. All right, all of this is crossed out. All right, if B goes 0 in S, I mean, all right. So look at S and B. They're anchored in. If Z changes, B is going to flip and change. If B changes, S is going to flip and change. Okay, they're tied into each other. We saw that because of the triangle. All right, his right here, up here. Because of this, we only have a certain number of solutions that that they can be. All right, so can't imply that zeta of S equal to 0 is 0. And we can't really say anything about B because we just all we dealt with is B equal to 0, but 0 is not a non-equivalent of 0. All right, so this is a false premise and a circular reference because what happened, or a circular argument, because we're saying that we can set it equal to non-critical 0 and then all of a sudden here say it's not a non-critical 0. We're going in a circle, all right? And doing that is like fitting a square peg in a round hole. All right, it's not going to go anywhere, and it's just going to disappear into the vacuum of space that 0 tends to lead to so often. All right, in this same case as here, we can't say anything about this equivalence or equality at 0 because of that third term. In a similar way, we're running into a problem with letting S equal to 0. Oh, man. Look, I'm trying to help you, Atiyah. Don't give me that look. I'm just kidding. All right, your first error, dude. Your first error is on page 3, line 15. 0, 0 does not equal 0. All right, so if B is 0, that doesn't equal 0. That's the premise. So we can't go. Now, now you saw, I'm assuming multiple typos, all right? I'm reading into it. So as written, it has an error, at least one error. That's the first error I found. By interpreting, assuming a typo, it gets other errors. By considering all that I can imagine, I don't see any way to salvage it. All right, I don't think there's a proof that come out of this. All right, as looking into it, so I don't believe he had a proof. Now, I do believe he is extraordinary individual. Was an extraordinary individual. I do believe also he is hopefully in an eternal place of truth and knows that what we're talking about was something we probably should have done when he was in this world. Point out error and and everyone can get back to work. Good. Speaking of work, so this is what we're going to do in the next video. Everything we just did, we're going to do to myself and my co-authors. We're going to go through the paper using all of your counter arguments and some others that came from mathematicians, some email. We're going to go through it, and we're going to take this little sheet of paper, and maybe at a little time I might do a little drawing of Greg, Danny, and me. I don't know if I have time, and I don't have pictures of Greg. I'm gonna email him just to see. Get a little pictures. I'll do a little goofy drawing of us, and then we're gonna go through with all the counter arguments in the paper that have been brought against the paper, and we're gonna see. And we'll give our response as well to what they are. Again, the reason I'm doing this is because it's going to give you the tools to actually give good arguments to not only our paper but also others. It's going to help you to refine your own proofs, and hopefully as you come across other Riemann hypothesis proofs or in general, you may be better equipped to see, all right, what are we looking for in their proof? Does it do this? Does it accomplish what it's set out to do? And like I said several times in this video, is it okay to make mistakes? Yes, it is okay to make mistakes. Do we learn from our mistakes? Do we fix the mistakes? Do we admit the mistakes? That is equally important. And with that, I hope you all have a very good evening. Goodbye.